Hi, I'm Michael. I'll be talking on LVM Cannon, which is a tool we use to reduce non-semantic differences in modules before diffing them. So this is a diff of an identical LLVM module, which has undergone two different passes. It's actually, in fact, a pixel shader. And we use those diffs to see what was changed by a given pass, and sometimes for debugging purposes. And reasoning for that many differences takes a lot of time. This is mostly because many of those differences are purely cosmetic and carry no semantic meaning at all. These are such differences as instruction order, value names, basic block names, and sometimes redundant code. So, encouraged by Priyan Lotfi's talk on Mir Cannon, we wanted to create a tool that would automate the process of reasoning for that differences. So, we needed a simple tool that would make comparing semantic differences between two modules easier. And we wanted this tool to reduce non-semantic differences. We wanted the tool also to process one module at a time. So we could actually leverage existing diff tools and use the same kind of workflow we used before. So therefore, the tool should transfer a module into a canonical form. Because the idea is that the canonical form, when we use the canonical form, two semantically identical canonicalized modules should show no differences when diffed. And more importantly, when the modules are actually not identical, the semantic differences should stand out. So we looked on the diffs, and we found out that one of the major factors influencing the diff is the instruction order. So we have started with instruction order, and we've made two bold assumptions. One is that, well, because two modules that we want to compare really come from just one module after given transformations, so we made the assumption that side effects should be roughly the same, the side effecting instructions. And we also made the assumption that the control flow graphs should be also similar. So we got an idea that we could use a method of def use distance reduction to kind of reorder instructions. And what we did in LLVM Canon is that, first of all, we collect all of the instructions with side effects and return instructions. And then we just walk through those instructions with side effects top down. And on each instruction, we walk through their operands left to right. And as we walk through their operands left to right, on each operand, we bring their definition as close as possible to the using instruction. So I'll walk you through the whole process step by step to just see some kind of edge cases. So this is exactly the same code snippet you've seen in the previous slide. And so we actually start with this first side effecting instruction, which is that star you see in green. We are not moving side effecting instructions. We don't want to change semantics. And we select the first operand of that side effecting instruction, which is instruction C. And we just simply move it closer to the user. You may see that actually the def use sequence right now is broken for the C operand in the instruction X. But that's just temporary, so trust me, it will get fixed in a moment. And then we take the first operand of the instruction we just moved, so of the instruction C, and that operand is T1. And we do exactly the same thing. We just move it closer to the user. And now you see that the def use sequence is actually broken for T1 operands in instructions A and B, though again, it's just temporary. And we do exactly the same thing. We select the second operand in the instruction C, which is instruction B, and we move it again closer to the user. Now you see that actually the def use sequence is repaired because, well, instruction B goes under instruction T1. So for the T1 operand, it's just repaired again. And then we select the first operand of the instruction we moved, so the instruction B. We take the operand A, and we do exactly the same thing. We move it closer to the user, and now the def use sequence is repaired for the operands T1 instruction A. So we select the first operand and second operand in instruction A, which are T1, and we don't move it because T1 was just moved before. And then we go down back we select the second operand of the instruction B, which is T1, and again, we don't move it, we move T1 before. And we repeat the whole process for every single operand in all side-effecting instructions. So we go through the side-effecting instructions top-down, and their operands left to right. So as we got the reordering algorithm kind of working, we decided to focus on the second thing that impacts the diff, which is value naming. And well, we kind of started with kind of pretty basic, trivial approach. We just numbered all of the values top down. We were kind of hoping that maybe after reordering, those values, I mean, the order of the instructions could be used as a kind of a seed for instruction naming. However, well, it didn't really work. The thing is that as you insert, as some kind of transformation inserts one more instruction wherever in the file, it just kind of increments all of the numbers for all the instructions down from that place. So we get an idea that we could actually use a bit of a different approach, something we called graph naming. And graph naming distinguishes two types of instructions. The first type are initial instructions, which are instructions which have only immediate operands. And in case of initial instructions, we actually first collect all of the initial instructions, and then we collect all of the outputs, so all of these side-effecting instructions which use the given initial instruction. And then we take the positions of those side-effecting instructions into consideration to sort the initial instructions. And then we number all of the initial instructions. And the second type that this naming method distinguishes are regular instructions. And in case of regular instructions, which are the instructions in green you see, the idea was that we wanted the difference in the upper part of the file, so the difference in the diffs, we wanted the difference to be reflected on the output instructions. So we've put, in case of regular instructions, we are just putting the names of the operands in the name of a given instruction. The thing is that, well, it also didn't kind of work. Well, so for initial instructions which had the same users but different opcodes were getting the same names. And in case of regular instructions, first of all, this naming method just generated pretty long names. And the second thing is that, well, differences in diffs were in fact reflected in the side-effecting instructions in their names. But not only there, they were also reflected in all of the instructions between them. So it actually polluted the diff, and it did the opposite thing we wanted to actually achieve. So we've changed the naming method, and this is the naming method we use now. It distinguishes three types of instructions. So there are initial instructions, again. However, initial instructions names consist of three parts. The first part is a hash, which we calculate considering instructions opcode and something we call the output footprint. And the output footprint is a vector of unique indices, so a distance from the beginning of the basic block, of output instructions. So let's say this being said, so as we get an instruction which is used by outputs 5, 7, 9, and 11, so this would be the integers would use to generate this hash. And then we have the second part of the name, part in green, which is the Kali name. We only include that in case of call instructions, obviously. And then we have a short operand list, which we in fact sort when an instruction is commutative. The second type of instructions we distinguish are regular instructions. And now things work differently. The thing is that, so again, we've got the hash. The hash is calculated considering instructions and its operands opcodes. Then we've got the Kali name, which is, of course, obviously only included in case of call instruction. And then we have something different. We have the operand list, though it's a shortened version. So in the operand list, we have the OP, then the short hash, but we are not including the part in the parentheses in this list. I'll get to that later. And we have the third type of instructions, which are output instructions. And these are instructions with side effects. And well, some instructions with side effects don't have names. So in case of those instructions, we just take their relative operands. So 1 or 2 instructions up from the instructions. And we name them exactly the same way as regular instructions. But we also include that part in the parentheses. So actually, by looking on the output instructions, you could see how different definitions, how differences in definitions impacted that particular output. So, well, you can by just looking at an output, we see what impacted the semantics in the diff. So these are all of the 3 naming methods. So instructions, and the lines in red are initial instructions. The lines in green are regular instructions, and the line in blue is the output instruction with the third naming method. So this is the diff I showed you in the very beginning of the presentation. So after applying all of the canonicalization techniques, we end up with a much cleaner diff, which is this one. So besides that, of course, the canonicalizer also does many different things. It names basic blocks. So for naming basic blocks, we just go for each basic block, and we generate a hash, which just considers all of the instructions opcodes in a basic block. We also just trivially number function arguments. And also, we sort values in phi nodes. So after naming the basic blocks, we just take a phi node, and we just sort the values alphabetically. Somebody also proposed that maybe we should remove duplicate values in phi nodes. However, I don't know, well, it's a canonicalizer. Maybe some kind of a pass or transformation adds duplicate values to phi nodes. So in fact, the canonicalizer should actually make that stand out so you could actually see that something is, well, wrong, and maybe change something. And considering the redundant code, we also think that it's actually beyond the scope of this project. There are different passes which remove redundant code. So we didn't want to focus on that. Many people also asked on the mailing list, why don't we actually integrate the LLVM Cannon with LLVM Diff? So the thing is that we also wanted to use LLVM Cannon to spot differences, to spot how a module changes by just looking at one file. And this is obviously not the same thing as Diff does. We wanted to leverage existing Diff tools. Everybody's got his favorite Diff tool. We didn't want to change that. However, LLVM Cannon could be used as a pre-pass before using LLVM Diff. And I just prepared 2 pretty short code snippets. They're semantically equivalent. The only thing that's different is just the ordering of instructions. And in fact, when you diff the files in LLVM Diff, well, you get some differences. However, when you run the LLVM Cannon before running LLVM Diff, you end up with 0 differences, which is, well, obviously what should happen. I'd like to thank Tpojan Lotfi for giving us a bit of a head start on canonicalization techniques, and for his talk during the 2018 LLVM on Cannon. You should definitely check out his talk. I'd like to also thank Radosław Drabinski, who gave the idea for this project and allowed me to work on it, and Julia Kowal for spending her time on the project and reviewing the code and testing it. I'd like to also thank the whole LLVM community for excellent code review on Fabricator. You may check it out, actually. It's not yet checked in. It should be in the very near future. And also, I'd like to thank everyone for coming to this talk. Now we can, well, if you have some questions, you may ask me. Thank you very much.
Any questions?
Hi. I was curious if you ever run into cases where you want to actually go back to the original uncanonicalized files to figure out what actually changed? Or is it enough to go, oh, okay, I see what the small change is?
So actually, well, sure, there were those cases. Well, it only kind of goes in the one way. You cannot really go back with a canonicalizer, though. But it may be actually interesting to check that. I haven't encountered personally any cases like that.
It seems like what you might want to do is like be able to go back to the, like I imagine you could maybe highlight the places in the original code that changed after the diff, right?
Yeah,
Maybe like
well,
take the
you
diff
could-
and post-process it going back
you
to
could
the
definitely do
original
that,
file
yeah.
or something.
Yeah, but I haven't done it. Yeah. No. Yeah.
So I was just thinking about corner case. What about that code that is not used anywhere? Are you ordering this in any way to make it consistent, or it's just left without any changes?
So in case of that code, if you just run this pass, it should go on the top of a given basic block. The thing is that if you've got any different passes to do that, so it should get removed. So, well, we're not doing anything specific to that code, but after reordering, it should just be on the top of the basic block. Though it's not canonicalized in any way. There's
Right,
no
so
special-
if there will be like multiple dead values, they won't be
They won't
ordered.
be canonicalized, yeah, because
Okay.
we are hoping for different passes to kind of remove them.
Okay, thank you.
Hi, sorry if I missed this in your talk. I'm wondering if you've thought about more fine-grained diffing than on the line level. Maybe instructions are the same, but the operands are different, stuff like that.
So could you repeat that question?
Sure, maybe you have the same application of a function
Yeah.
into IR files,
Yeah.
but the operands are different. So just showing the diff of the operands.
So in case of the difference in the operands, and you mean those differences in depths, right? So let's say you get some differences just operands in a given definition. So by using the canonicalizer, you could actually just take a look on a output instruction, some kind of instruction which has side effects, and you will actually see those differences in the defs reflected in the name of that side effecting instruction. So this is one of the goals of that project. So not only it canonicalizes the file, but also it shows you the differences in the name of an output. So, well, it's just obvious what happened.
I see. I was thinking a bit more fine-grained, like not less than line level, maybe?
Well, yeah, well, we could do that. We haven't done that here, yeah.
I was curious about like using canonicalization techniques as a way to aid like other optimizations, like maybe peephole optimizations or outlining, where let's say you have like a more consistent like layout of instruction orderings across a bunch of functions, or you like can canonicalize in a way that like a certain peephole optimization can more effectively process. Have you like?
Yeah, I mean,
I think that would be a good
sure.
future work.
It could, yeah, we haven't thought about it. I'll reach out to you after the presentation, but sure, it could be done.
Hi, thanks for your work in the talk. I was wondering what your personal experience has been with any canonicalizations performed by this tool that ended up hiding a bug. Have you not hit that problem, or I was just wondering what you've seen.
So I must say, well, well, definitely, it's pretty cool to use this tool for shaders and that kind of stuff. Well, I don't recall like I don't have like an example to tell you of a particular bug that was found using the tool. Though you may also use this tool. It's pretty cool to use this tool for C files compatible with Clang to LVM-IR. It doesn't work that good for C++ files, so maybe I should kind of spend a bit of time working on that. The one thing, so the tool doesn't reorder side effecting instructions, only non-side effect instructions. So if anyone has some kind of ideas, interesting ideas how to do that, please reach out to me after the presentation, because that's one of the things we're experimenting with.
Any other questions? Okay, so let's thank the speaker.